So in this presentation, I will attempt to introduce you to the concept known as flagging in radio astronomy. All radio astronomy data will be contaminated by various spurious signals that are completely unrelated to the science data you're interested in. These interference signals have to be flagged out before science data processing, such as imaging a radio source, which makes flagging your data generally a very large part of your radio astronomy data processing. The presence of bad data in your observation will negatively affect both the data calibration solution as well as the interferometer amplitude response, reducing the final quality of the science data you output. During the process of flagging, you will view your data, most generally from calibrators, and you will only focus on removing bad data. And bad data we will classify as overpowering signals from terrestrial or satellite RFI. They will completely wipe out your faint signal that are buried in the noise and may also potentially negatively affect the sensitive electronics of your telescope, making that part of the data unusable. Secondly, we will find any erroneous data caused by instrument failure that must be identified and removed, as well as time ranges where cloudy conditions and other atmospheric effects or instrumental effects may affect your observational data. There is no single algorithm for flagging, and it is almost always very dependent on the data, as well as the type of science data processing. In this presentation, we go through the basics of flagging, that is in general good practice, and serves to introduce the newbie to the concept of flagging. Our basic flagging strategy can be described as, firstly, a single run where you flag out known channels affected by RFI, and this entails discarding channels that are always affected by RFI, as well as time ranges where satellites have traveled across the sky visible to our telescope, causing the sensitive electronics in the telescope to become nonlinear. Secondly, a repeat loop, where you use strong compact sources, such as primary calibrators, to identify instrument-related issues such as bad antennas, period of bad weather or other atmospheric effects, as well as general outlier points, which may be slew data that get included and needs to be removed, otherwise it introduces amplitude and phase errors. Care should be taken when flagging noising data. It is better to start with a strong calibrator source in order to help distinguish between bad data and uncalibrated or poorly calibrated data. A general rule of thumb is that antennas, channels, and time ranges that are bad for the calibrators, which we know are strong compact sources, will also be bad for the weaker science target, and the data is flagged out by default on all the targets in the observation during the calibration flagging cycle. Only once calibrated can you proceed to very carefully flag bad data on the target source itself. This can be performed before imaging, but the user should note that the target source is generally unknown in character and may not be a point source, so please take care. Interference by satellite and other terrestrial emitters, such as cell phone towers, are a constant in the observed radio passband and must be flagged starting with some fixed masks that flag out these known RFI channels in the observation passband. These channels are generally very well known per observatory, and for Meerkat, this information is provided by the SARO service desk. The amount of RFI contamination will depend on the frequency range. The Meerkat L-band loses a significant amount of channels due to satellite RFI, while UHF is much quieter since analog broadcasting has gone out of fashion. The 1 to 2 GHz frequency range is preferred by communication broadcasters since it passes through obstacles such as walls quite easily and is not greatly affected by weather conditions or solar activity. These RFI-affected channels are fixed and well known, and in general can be flagged out by default. The Visualizing Meerkat Data Notebook details the RFI affecting Meerkat L-band and can be found in the Meerkat Cookbook, while the step-by-step notebook L-band RFI frequency flagging illustrates the RFI flagging for Meerkat L-band and is available in the Workshop Cookbook. The Workshop Cookbook also contains the example Flagging MCAT L-band, which is a convenient script for applying standard L-band flagging in one step. Since the antenna-based calibration solutions are determined from observation of calibrator sources, all bad data for a calibrator source should ideally be removed before determining the calibration solutions. Calibrator sources are easier to flag because for the most part they are bright and you know what kind of source it is, and therefore you know what to expect from the visibility data. In particular, calibrators are compact or unresolved sources, which means the true visibility amplitude is independent of baseline and time, and the phase should be stable over frequency and close to zero after calibration. Also, remember that when you first view your data, all your data is going to be uncalibrated visibilities. So the safest choice is to focus on your primary calibrators, since they are best described and may already have spectral models that you can use to guide you. For Meerkat, all dishes have approximately the same sensitivity, and thus we anticipate that the uncalibrated visibility amplitude on your baselines should be close in value or approximately the same, while the uncalibrated phases should be fairly stable over passband, even though they may not necessarily be close to zero before calibration. Although different interactive flagging tools are available, for the initial flagging, the best approach is usually to first make several passes through the data, using various plotting and listing tools to identify the bad data. Once you have identified sections of bad data, you can then continue to flag them explicitly using flag data. This allows you to keep a detailed record of your flags, just in case you have to redo or undo flagging a little bit later. First off, we will check the phase stability both in frequency and time. If the visibility phases for a calibrator is not reasonably stable over time and across channel, antenna-based calibration is not likely to be successful. Plotting the phases over frequency for individual baselines, we expect to see graphs that show a consistent phase over the passband for all baselines, and if however the phase of a baseline is scattered randomly, one antenna in that baseline may be faulty, in which case it will be a good idea to check the other baselines for each of the antennas in that baseline pair to see which one of the antennas may be responsible for the error. Follow this up by inspecting the phase stability over time. If an antenna is in error, you will see similar discrepancies for the baselines of that antenna. Once the antenna has been identified, the antenna is flagged out. And please note, even if you see this distortions only on a single polarization for an antenna, continue to flag out the antenna entirely, both polarizations. Lastly, view the visibility amplitude, which for a point source should vary only slightly over channel and should be fairly well co-located for Meerkat. Plot amplitude over channel for all the baselines simultaneously. There should be relatively little variation of the visibility amplitudes over frequency. If one of the channels show large scatter, it is typically indicative of RFI in that channel. If this channel shows the same scatter for other calibrators, that channel is contaminated and must be flagged out. As satellites and bad weather passes over the array, the data over certain time periods during the observation may be affected. Plotting amplitude over average time makes it easier to identify these time ranges, which can then also be flagged out to prevent from negatively affecting the calibration solutions. Identifying bad channels and antennas in the calibrated data are flagged out by default, as we said, on the target source, since it is most likely to have the same issues. Now similarly, if the time range of bad data persists longer than a calibrator scan or over multiple scans, then that entire time range, including the scans for the target observation, need to be flagged out. Since it is generally easier to identify bad data after some calibration is applied, a good calibrator flagging strategy is to, after the initial uncalibrated calibrator visibility flagging step, use the cleaner calibrator data to calculate a calibration solution. Apply these solutions to your calibrator targets themselves before briefly re-examining the calibrated visibility data for the calibrator sources, in case there are more bad data that can now be identified and flagged out. Follow this by another cycle of flagging and recalibration, a rinse and repeat cycle. Thus, we use the calibrated data to identify more non-obvious potential bad data that is flagged in the raw data, and the cycle of calibration and inspection continues for a couple of rounds. Only once calibrated can you proceed to very carefully flag bad data in the target source itself. Before flagging the target source, it may be a good idea to look at the science target data and verify that there are no obvious spectral lines in the channels that you may now accidentally identify and flag out as bad data. Also, the science target are unknown in structure and generally extended. Care should be taken when inspecting science target data. And remember, do not reapply calibration to these targets after flagging. The flagging is for cleaning and imaging, not calibration. So let's summarize. There will always be bad data points in your data, and that will affect the calibration and data analysis. Most errors are due to instrumental failures, and almost all of these are antenna-based. Such faulty antenna errors will affect all baselines that include that faulty antenna. Thus, as a first step to radio astronomy data processing, we will always spend a little time simply looking at our data before doing anything. Looking for bad antennas, persistent bad channels across all spectra and windows, and other clear outliers. Once bad data has been identified, it must be flagged out to improve results. There are no cookie-cutter solutions to flagging. A few useful rules of thumb to remember is start your inspecting and flagging on the flux and bandpass or your primary calibrators as a first round. Care should be taken with the gain calibrators, since they are not necessarily point sources and may be partially resolved. It may be more advantageous to do a first round of calibration and applying those calibration solutions to the calibrators, before repeating the inspection and flagging second round cycle that will now include the gain calibration sources. If possible, err on flagging either all visibilities of the same time interval or flag data based on antenna. Rather, do not flag based on individual baselines. Always start off by visualizing your data first and trying to make several passes through the data. Average over time and frequency to get less noisy data displays. And once you have identified those sections of bad data, flag them out explicitly to keep a record of your flags. A couple of tutorials will help to cement the concepts presented. First off, you will visualize how much of the meerkat L-band spectrum is lost to RFI and which antennas or transmitters are the culprits using the L-band RFI frequency flagging notebook. For students new to GET and CoLab, please remember to visit the Soreo e-learning portal page and first work your way through the introductory courses for GET and CoLab before starting your tutorials. Next, start your own CoLab notebook in Google Drive and apply the flagging principles of the previous flagging tutorial to flag both RFI and bad data to another small dataset, an NGC dataset, before we will calibrate and image this dataset a little later on. And optionally, for those who have a little bit more experience, a tutorial to try your hand at starting pipeline processing by implementing the functionality in the example flagging script in Python to automate your basic RFI flagging applications. Thank you.